Section 13F, area of right triangles. There are two formulas for the area of a right triangle. The first one is 1/2 base times height, and the new one is 1/2 AB, the sine of C. There are three types of triangles. The first one is the right triangle, where it's easy to see why you could use the sine of C, because it's a right triangle. There's also an acute triangle, where if you dropped the height, we're building a right triangle, so we could use the new triangle. Or an obtuse triangle, where again, if you drop the height, we're building a right triangle. I'm pretty sure you know how to use the old formula, so let's look at the new formulas. We're not going to look at the right triangle one, but we will look at the acute and the obtuse. For the acute triangle, if you drop the height, you can turn it into a partial right triangle, or turn half of it into a right triangle, and use our right triangle properties to find h. So if you look at it, if we start from corner C, we want to find h, well, that is opposite over hypotenuse. So the sine of C is h over b. If you went ahead and solved for h by timesing both sides by b, you would get that h equals b times the sine of C. The other triangle is an obtuse triangle. So the original triangle is this part, okay, which is not a right triangle, but if we drop a perpendicular, there's our height, and we can just look at this little pink triangle and use that to find the height. Well, if this is our corner C, I think it's pretty evident that the blue corner plus this green corner right here must add to 180. So if the blue corner is C, the green corner then is 180 minus C, and we can go from that corner and use our trig function, which would be opposite 180 minus C, would be opposite, or h, over hypotenuse, which would be b. So the sine of 180 minus c is h over b. And again, we could solve for h, and we get b times the sine of 180 over c. Basically, this just shows us that the height will always be the base times the sine of the angle we can make using the height in one of the corners, or the height in an exterior corner. Okay, so both of them, it's b times the sine of some angle for h. Well, that leads us to our old formula, which is 1/2 b times h. Let's go ahead and use this version and substitute in for h. And we get area is 1/2 the base, and now h is b, the sine of C. So by substituting in h for h, we get 1/2 b times b, the sine of C, which is almost our new formula, but our new formula is a times b, the sine of C. But remember, this b was the base of this, was the hypotenuse of this little triangle, okay, and then this was actually the base of the full triangle, which is technically a. So using the trig functions, we are just solving for our missing h, plugging it into the original formula, and that's how we get the new formula. The question is, how do we use that new formula? So here's an example. You may want to pause to copy it down. And we have some triangle with a base of 30. We don't know the height, but we know we have a corner of 40. So I'm going to think about the old formula, 1/2 base times height, and use my trigonometric functions to solve for h. So I'm just going to look at this part. If I went from 40, h is some trig function of 40, which is h, which is h over b, which in this case is 20, and then since it's opposite over hypotenuse, that's going to be sine. Okay, and so again, go ahead and solve for this h. We're going to times both sides by 20. And we get that h equals 20 times the sine of 40. Now, if we plug that into our original formula, that is 1/2 b, which is the base of the real triangle, which is 30, times 20, the sine of 40. And if you notice, that is 1/2, this is the base, b. Here's our a. Now, this is supposed to be AB. Basically, it's just a side and its opposite angle. So BA, the sine of C. Didn't really matter that these two switched. And if you put that in the calculator, you should get a height of about 12.8, because remember the height is 20 times the sine of 40, or 12.8. Times that by the base and 1/2, and you get an area of approximately 192.8 units squared. Again, you just have to plug and chug into the formula, but I'm attempting to show you how this h is really just made up of irregular trig functions and ends up fitting the formula 1/2 a b, the sine of some corner c. Next, we're going to talk about the cosine rule and the sine rule. The cosine rule is a squared equals b squared plus c squared minus 2bc, the cosine of a. A, b, and c, the little ones, are just the sides of the triangle. And you're going to have one angle that's across from the little a. So it doesn't really matter if you have a first, b first, or c first, but whatever goes on this left side has to be the side across from the angle that you're using right here. So for example, we're trying to find x, and we have two sides and an included angle. Since we're trying to find x, basically that's going to be our little a, or that will be the thing right here. And then these two will always be the b and c. So we plug in our formula. We have x squared equals one of the sides squared plus the other side squared minus 2 times the sides again times the cosine of the included angle. If you put that in your calculator, you'll get x squared is about 614.359. I wouldn't write that out. I would just put it in the calculator, and then to solve, to get rid of the square root both sides, and x is about 24.9. So it's identifying where you need to plug in and then simplifying. We use the cosine rule in two cases. Those cases are when we have two sides and an included angle, like I just showed you, or if we had all three sides, we could go backwards and find a missing angle. And I'm going to let you look at your book for those examples. But again, it's plug and chug into the formula and use algebra. The other formula is the sine rule. And it's the sine of some angle A divided by its opposite side equals the side of B divided by its opposite side, and the sine of C divided by its opposite side. And basically, you just pick an angle in its opposite side and set it equal to another angle in its opposite side. So you pick 2 out of the 3. You could also put the A, B, and C on the top and the sine of the corresponding angles on the bottom. It doesn't matter in which way you use this formula. Let me show you an example. So we're going to take the same triangle, and I'm going to round this 24.9 to 25 just for simplification. And this time, instead of finding a missing side, which we could do, we're going to go ahead and try to find a missing angle using inverses. So we're going to plug it into our formula. I have the sine of some angle 30 right here divided by its opposite side, 25, and that's going to equal the sine of the angle we're looking for, theta, divided by its opposite side. Now we use some algebra 1 and cross multiply and solve. So we have 25 times the sine of theta equals 40 times the sine of 30, which is just 25 times a variable equals 40, or equals a number. And in order to solve something like that, we divide both sides by 25. And we will get the sine of theta equals 40 the sine of 30 over 25. In order to solve for this angle right here now, we need to take sine inverse. You could put it in the calculator just like this, but it turns out in this case, 40 the sine of 30 over 25 is a nice decimal, so 0.8. So you could also put it like this, and you get about 53 degrees. Again, this is only one out of the 2 ways to use this formula, but there are other examples in the book. And let me have you write down when you use it. In this case, you use it if you have one side and 2 included angles, or one side and 2 angles, or for the example that I just showed you, 2 sides and the non-included angle. So again, we have side, side, included angle versus side, side, and not the angle in the middle. The angle in the middle would have been right here. So I definitely want you to try these problems and use the book to supplement for the other versions you have not seen examples for. Thank you.